All right. Hello, everyone. I hope everyone did great on their first exam. Congratulations. It is not easy to be in this course. So, if regardless of how you did, whether you did good or whether you did bad, and by bad I mean not ideal, um, don't worry. You still have plenty of exams, and we'll get into all of that and reviewing for next week. Sorry, next exam in the future. All right, so like always, I'm going to start off with what we covered last week, which is Fisher. And since last week, last Wednesday was the day of the exam, um, we're always going to have an exam review. So usually in the peer tutoring lab, it gets a little bit busy. But if you guys ever want a more review type of environment, please come in person on those exam days. I know everyone's busy doing their own thing, but it could also be a Q&A session. Really, I don't have any thing prepared. That's for the exam reviews that the SSC provides, or peer tutoring rather. So you can always attend those, but these weekly reviews on the day of the exam will be more of a Q&A session. So today we are going to recap exam 1. We're going to take a look at what's coming next in exam 2 or unit 2. And then we're going to start off with chapter 4, talking about all those things: initiation, propagation, termination, as well as free radical halogenation, specifically chlorination and bromination. And then we are also going to get into SN1 and SN2. And then next week, we are going to review SN1, SN2, and start on E1, E2. All right, so let's get to it. Okay, so just a quick overview of exam 1. Let me zoom in a little bit, center that a little bit. Okay, so this is your first time taking an organic chemistry exam. It is not a easy course, right? If you're going to med school, some people call that the weed out course. But hopefully, as you are, going through the course, you'll come to realize, or hopefully, you'll feel more confident with the course material, and it won't feel like the weed out course. And that's a whole nother topic. Whether you get an A or a C, you shouldn't base your medical aspirations on this course solely. Anywho, this course is also different from general chemistry. As you guys know, general chemistry has a lot of different mathematical equations and functions you have to use. Maybe not so in Gen Chem 1, but in Gen Chem 2 especially, you have to. OChem, as you can see, there's rarely ever any math. So, that could be a good thing or a bad thing depending on how you look at it. It's also, as you take this exam, you're a sophomore, right? And in your freshman year, we had the pandemic, so you won't have that. You're still kind of getting used to taking exams in person, because most likely the last time you took exams in person was back in high school. So it could be a very drastic change. So, just keep that in mind, be understanding of yourself. And then regarding multiple choice versus free response questions, that could also be challenging for some people. Some people like multiple choice, some people don't. Some people prefer free response questions, some people don't. So depending on your style and the professor you may have, and what you have in what you covered in class, all of those variables could also play an effect. And then this exam, Unit 1, has challenging concepts that revolve around spatial awareness, such as shear conformation, Newman and Fisher projections, and even stereochemistry with wedges and dashes. That could be very challenging. Not everyone learns that way, and even if you do, it still might be challenging because this is still your first time exposed to this. So again, don't be discouraged if you didn't do so well. If you did really well, I'm really glad to hear that, and I hope you guys continue doing well. Um, always please feel free to let me know if these reviews are working for you. If there's anything I need to improve on, if I need to talk slower, talk quicker, faster. I am obviously making my own improvements as we go, as you'll see for this week's review. Um, and yeah, so another thing that I mentioned to a lot of students when they come in person, um, not for the exam review or weekly reviews, but drop-in tutoring, is that there's going to be different tutors, there's going to be different professors, different TAs, different SIs, different PLTL leaders. Everyone has their own unique way of answering organic chemistry material. Not everyone, not all of those could make sense to you. One approach may completely make sense to you. One approach may not, and it may confuse you rather. So make sure whatever is working for you, whatever modality works for you. If you really like your professor's way of teaching, or you really like PLTO versus SI or peer tutoring, specific tutor, I recommend you stick with that. Obviously, because if you listen to all sorts of opposing views, it could get very confusing and challenging. So I understand. So again, choose whatever helps you. If you do better studying alone versus studying in a group, so whatever works for you. Okay. All right, so some things to think about is there's going to be an exam 2 and a final exam, and I believe the final exam replaces the lowest exam grade. So that could be something to look forward to. You still have lots of quizzes to increase your grade if you're on the lower end. And you're going to have different concepts. Maybe Unit 1 material was really difficult for you, but Unit 2 and Unit 3, you'll find it very easy. I personally found Unit 1, Exam 1, the most challenging in all of OCHEM 1 and 2. So in my mind, the worst is over. It only goes up from here. But for other people, each person has their own opinions, of course, and each upperclassman will say different things. Exam 1 could be difficult because it's new and different and spatially difficult. Exam 2 could be difficult because there's a lot of subjective mechanisms and reactions that could go either way. Unit 3 material could be difficult because there's lots of reactions that you have to know and a lot of mechanisms, so that could be challenging. OCHEM 2 could also be more difficult than OCHEM 1, which I personally feel OCHEM 2 is a lot more easier because it's more fun. And yes, that's right, I use the word fun because it is fun. So yeah, and another thing is you now know what to expect. You now know how the exams are, you know how the quizzes are, you know the type of wording and language they use to answer questions, you know the difficulty of questions, you know the format, if there's true and false, matching, pre-response, etc. And you know how to study, hopefully. And if one study method didn't work, obviously try the next. If one resource didn't work, try a different resource. If one tutor didn't work, try a different tutor. If peer tutoring works, but PLTL didn't work, stick with peer tutoring. Whatever works, and that goes into utilizing your resources. make sure you are aware of all the resources and make sure you're using those to the fullest so you can get, you know, the most out of your studying. And lastly, the scale is very generous, okay? And I say this because a lot of people or a lot of students will, you know, freak out if they, you know, get a 70. But a 70 is a B plus. It's not a C minus. That's why OCHEM is very generous, and you have lots of resources, lots of tutors, lots of help and practice problems to get you through this course. So please don't worry. It's my duty to make sure you guys are not worried about this course. I want you guys to worry about other courses, but not this course. OCHEM should be stress-free. Okay, and if it's ever at a point where you are struggling, please reach out to me. You know, you can always find me in the drop-in tutoring, peer tutoring lab. I work Mondays and Wednesdays from 2:30 to like 6:30. So feel free to talk to me if you're ever struggling. All right, so enough about that. So looking forward to exam 2, you finally get 2 reactions, which is probably what you have heard about OCHEM before taking this course. And in this unit, there's going to be a large concept. So in exam 1, we had very tiny multiple concepts. You had hybridization, resonance, sigma pi bonds, functional groups, IR, chair, Newman-Fisher, isomers. You have lots of things. In exam 2, you have very brief ones. You have free radical halogenation, you have stability of carbocations, carboanions, and radicals, and you have your 4 mechanisms. Okay? In the past, sometimes they also include alkenes, and in some years they didn't include that. They put it for unit 3, so you'll have to see what your professor says. Another thing, like I already mentioned, that this exam can be subjective, okay? That means, again, different tutors and even different professors may have varying opinions on how a reaction will take place. Please understand that these reactions will have a percent of one mechanism and another percent of another mechanism, okay? It is not always all or nothing. There's always going to be a small percent of another reaction likely to occur. And also, please go with whatever your professor is saying and not whatever the internet is telling you or what a YouTuber is telling you, because your professor is the one that's grading, right? So if you put down something your professor says and you get it wrong, you can obviously go into office hours and tell them, this is what you taught me, why did I get this wrong, etc. Okay, you can always argue your case. All right, so we're going to look at the syllabus real quick. So you guys took your exam last Wednesday. You had that following Thursday to introduce chemical reactions and free radical halogenations. And then you had another lecture yesterday continuing the conversation about chemical reactions, right? And then today is the weekly review. We're going to review free radical halogenations as well as get into SN1, SN2. And then tomorrow, you'll talk about alkyl halides, nucleophilic substitutions. And next Tuesday, you have a quiz. I'm not sure what the quiz is on, and I'm not sure if each professor has the same quiz or the same day of the quiz. This syllabus is from Dr. Panapatia, so if you have a different professor and your syllabus does not look like this, obviously refer to your own syllabus and not this one, okay? But just to give you a preview, this is free. Chapter 4 is the halogenation introduction. Chapter 6 is going to be the bulk of this unit, which is going to be your 4 mechanisms, which is going to be SN1, SN2, E1, and E2. We'll talk about what those terms mean and what they are. And then chapter 7 and 8, you'll get into alkenes. I'm not, like I said, I'm not entirely sure if alkanes will be on your exam. I would assume they are because you have 4 lectures over it, um, and you have 4 lectures over the mechanisms as well. So about the same time, and in fact, even more time than the mechanism. So you'll have to refer to your professor on what's included and what's not. And then November 3rd is your second unit exam. And then I don't have the rest of the syllabus pasted here, but you don't have a third exam. You'll have a unit 3, but that unit 3 material will show up on the final exam. Okay? So just be aware of that, and we'll get into that once we finish exam 2, and we'll talk about exam 3. Okay? But for now, okay, looks like there's no questions, so I'll move on. Okay. So let's get into chapter 4. Okay? So chapter 4, we're going to start off with 3 terms, which are carbocation, carboanion, and radicals. Okay? Hopefully some of these will seem familiar. Maybe this was briefly mentioned in the exam review that Ria and Justin held. And if not, you should know the terms cation and anion from general chemistry. Okay, cation is obviously the positive charge, and anion is the negative charge. And carbo, take a guess. It's going to stand for carbon. Okay, so that means I have a positive charge on a carbon or a negative charge on a carbon. Okay, now radical is maybe a term that you haven't heard before. But to put it into simple terms, a radical is a single electron that is bonded to your atom. Okay? It is a single electron bonded to your atom. Okay? So in a lone pair, it's technically 2 radicals. Okay? And a bond, again, is 2 electrons, aka 2 radicals. Okay. So I would, refer to your PowerPoint and lectures for the exact terminology and all the different ways radical is defined. Just in case. So just a disclaimer. If anyone tells you anything, whether it's me or another tutor or anyone, always, fact check with your professor and or like another professor or the textbook. Just make sure everything is aligning. Okay, so we will get into, so these 3 have there's ranking questions in this unit. There's going to be ranking questions in every unit, but the ranking questions in this unit, some of those questions will deal with stability of carbocation, stability of carboanion, and stability of radicals. Okay, so we're going to talk about carbocation and radicals because they have the same stability trend. Okay, you'll hear that word trend a lot, and you can use this trend as kind of a guide to help you solve stability questions. Okay, so let's zoom out and let's look at our problems. So these aren't for 5 individual atoms or molecules. These are rather, okay, and sorry, I made it a little bit too big. Let me see how it looks. Okay, so let me see if I can draw on this. So draw, black. Okay, perfect. I'm just gonna undo that. Okay, so again, carbocation and radicals have the exact same stability trend. Okay, so next to each of these, I'm gonna put a radical, and this is the symbol for radical. Okay, and let me actually draw the symbols for all 3. So it's, I'm not sure why that's happening. zoom out. So this is a carboanion, this is a carbocation, and this is a radical. Okay? So next to each of these carbocations, I'm going to draw a radical. Okay, hopefully that won't be too confusing. Okay, so when we look at this, hopefully we can recognize that this is called a benzene, and this is a CH3, a methyl. Okay, so we have a charge on our methyl that is bonded to this benzene ring. Okay, and hopefully you will be able to identify that this charge, whether it's any of these, can technically resonate with this. But in this case, we're going to solely look at carbocation and radical. Okay, so this charge is able to resonate with 3 different double bonds, giving 3 resonance structures, right? So that it is very stable. As opposed to this, there's only 1 resonance form. Okay, so each of these have their own terminology, which I will define. Let me maybe zoom in a little bit. Okay, so this one is called benzylic. Okay, let me see. Bell right on top. Okay, I'm not sure why it's shifting, but yeah, please bear with me. So it has the benz part, the prefix, and ilic kind of exemplifies, there's resonance. Okay, this one is called allylic. Okay. So allylic is a single resonance structure, where benzylic is resonance within a benzene ring. Okay. So benzylic is obviously greater than allylic, and next we have this structure. Let me zoom out real quick. Let me undo. Draw. Select. Not sure why this always happens. Give me 1 second. Okay, there we go. All right, so real quick before we get into the rest of these. Okay. So right now I'm just gonna define them and we'll talk about what they mean. Okay, so this one is called tertiary. This one is called secondary. This one is called primary. And this one obviously is methyl. Okay? And again, this is the trend of carbocation and radical stability. Okay? Now tertiary is also denoted as 3 with a degree sign above it. Secondary, same thing, 2 degree, 1 degree. Okay? But we don't obviously say 3 degrees, 2nd degree, 1st degree. We say primary, secondary, tertiary. Okay? Now let me explain how we are getting 3, 2, 1. Okay? And I'll draw right here. So let's say we have this structure, okay? Or actually, that's too much. Say we have this structure, okay? So if I'm looking at this carbon, so I draw an arrow to the carbon I'm looking at, and I circle all of the other carbons bonded to that atom, that carbon. And I have 3 carbons bonded to that single carbon. So I'm going to label this as tertiary, or tertiary. Okay, now let's look at this atom. So that carbon is bonded to this carbon right here and this carbon right here. Okay, so that's 2, right? So this one is known as secondary. Now let's look at all of these. Okay, so all of those are solely bonded to one carbon, and one carbon, right? So all of them are considered to be primary. Okay? So that's how you define if it's a primary, secondary, or tertiary carbon. Okay? Now we are putting a charge, a carbocation and a radical at that tertiary carbon. We're putting a charge on the secondary carbon, and we're putting a charge on the primary carbon. Okay? And then obviously this carbon is going to be considered a methyl carbon. Okay? So don't get methyl and primary confused. Okay? So even though this is bonded to a methyl, this carbon is bonded to one other carbon, whereas this carbon is not bonded to anything. Okay, it's a single methyl group, which really is just a dot. Okay. All right. So that should explain what tertiary, secondary, and primary means. Let me explain why this is the trend, though. Okay. If I can know how to zoom out real quick. Okay. There we go. All right. So again, let's look at this. All right. So benzylic and allylic have resonance, right? So these two have resonance. Okay, and as we know, resonance is very stable and helpful in stabilizing our charge, whether it's negative, positive, or a radical. It is going to stabilize that charge because it is spreading that charge very thin across a larger surface area. Okay, weakening the instability of that charge. Now, the reason why tertiary is the next most stable structure for carbocations and radicals is going to be based on based on this concept. So let's look at this tertiary molecule, and let's look at this positive charge. Okay, so there's going to be a term called electron withdrawing and electron donating. Okay, electron withdrawing groups and electron donating groups. Okay, and this is a organic chemistry 2 concept, but it also applies here, and this will make a lot of sense using this terminology. Okay, so again, electron donating group and electron withdrawing group. Okay, so it's not too complicated. So methyls, these are all 3 methyls, right? Methyls are going to be electron donating groups, okay? So again, CH3s are electron donating groups, okay? So they have electron clouds or electrons that they can donate their electrons to, okay? So they are donating their electrons to this carbon, which is lacking electrons. Remember, a positive charge means it's lacking electrons, and negative charge means it has too much electrons, okay? So if I have 3 methyls stabilizing a single carbon, that is very helpful, right? It's going to provide stability, okay? Think of this as inductive effect. But where inductive effect, we looked at halogens sucking in electrons, right? So as like a magnet. But methyl groups are electron donators. So they give electrons to this positive charge. If these methyl groups were fluorine groups, then this tertiary carbon is going to be very unhappy because they are sucking in electrons that the carbon already lacks. Okay? Now let's look at a secondary carbon. Okay? So obviously, 2 sources of electron donations versus 3 sources. The 2 sources is obviously going to have less, stability, right? There's only 2 ways that carbon can stabilize itself. And then when you have a single electron or single methyl, it's going to be even less, okay? So yeah, so that's the concept of why tertiary is better than secondary and why secondary is better than primary in terms of carbocation and radical. We'll talk about carboanion later, okay? So I know that was a little bit lengthy, but that is carbocation and radical stability. Now let's look at carboanion, which is almost similar with a few exceptions, okay? So first off, the trend is as drawn, as follows. And then again, this is benzylic, allylic, methyl, primary, secondary, tertiary, okay? Now, benzylic and allylic, regardless of positive, radical, or negative charge, they are all going to be stabilized by resonance, okay? So resonance are these 2, benzylic and allylic. So those are always going to be number 1 and 2 for carbocation, carboanion, and radical stability. Now, it's the last 4 groups that are different from each other. In the same example where I gave up here regarding, all of these, let's say I have, let's say I have a negative charge instead, and my carbons are providing more negative charges, that is going to be not helpful, okay? We don't want negative charges. So that's why when we have this and we only have 1 source of negative charge coming, it's not as bad as 3 negative sources helping hurting that negative charge, okay? So it has a inverse effect compared to positive charges. That's why it goes methyl, primary, secondary, and tertiary. Okay? Again, this is a trend that will help you answer any ranking or any regular stability questions. Okay? I know I talked a lot, but I want to make sure I'm very detailed in teaching you this concept so you don't have any questions about it, and once you know it, you'll know it for life. Yes, for life. So if I ask you in 10 years, I need you to tell me this concept. Okay? All right. Now, we'll look at something called BDE. And no, I'm not talking about that BDE. I'm talking about bond dissociation energy, okay? Which essentially translates to how much energy does it take to break a bond, okay? And the trend for this is going to be the exact opposite of radical stability, okay? Let's think about that for a second. Radical stability is up there. It's benzylic, allylic, tertiary, secondary, primary, methyl. So if it's the exact opposite of radical stability, it's going to be what? Yep, that's right. You guessed it. It's going to be methyl, primary, secondary, tertiary, allylic, and benzylic. Okay, so let's see if you notice something different that I didn't include in carbocation and carboanion stability. Okay, that's going to be the first structure we see in the BDE example. Okay, we have a double bond and a charge directly bonded to that double bond. Okay, so hopefully in lecture you guys have already talked about this. If not, any guesses on what it is? Okay, well, if you guessed vinylic, you would be absolutely correct. And that's exactly what this is. So this structure is called vinylic, or vinylic, or whatever. And then obviously this is methyl, primary, secondary, tertiary, allylic, and then benzylic. Okay. And the trend goes this way. So it's the exact opposite of our radical stability trend. And again, radical stability and carbocation stability are similar, or the same, not similar. They're the exact same. Okay? So BDE, again, it stands for bond dissociation energy, and not the other BDE. It is how much energy it takes to break a bond. So the more stable your bond is, the less energy it requires to break that bond. Okay? And we talked a little bit about this in ranking acids and stability of those structures. Okay? Stability and energy have an inverse relationship. Okay? And that statement is not an end-all be-all because chemistry is subjective, and depending on what you're looking at can change the statement. Okay, and that's a good rule of thumb for all of OChem, which is don't apply broad statements like that to every example you see, especially in this unit. You absolutely cannot look at broad statements and apply it to a generic example, a generic reaction, because these examples, the problems in this unit, you have to take it up one by one. Okay. So the reason why vinylic, again, vinylic is a charge. So in this case, it's a radical, but it can also be a negative charge or a positive charge. Okay, those charges are very unstable when placed directly on a double bond. Okay, and actually, I'm not entirely sure about a negative charge because some professors say a negative charge on a double bond in a vinylic position is actually stable compared to a radical and a positive charge. Okay, but let's ignore radical positive and negative charges and let's stick with radical positions. Okay, so vinylic is very unstable, which is why it has the highest amount of energy. It requires the highest amount of energy to break that bond. Okay, and that's the bond between carbon with a double bond bonded to the radical. Now, a methyl carbon bonded to a radical is going to be the next highest, and then a primary carbon, secondary, tertiary, in that order are the next highest. And then allylic and benzoic obviously have resonance, so they provide a lot of stability between the charge and or the radical. So it doesn't require a lot of energy. Okay, that's why the trend is opposite. Okay. All right, so I believe that should be enough on explanation regarding stability and BDE. If you have any more questions, please come and drop in tutoring and see if there's any confusion. All right, so moving on, I briefly talk about initiation, propagation, and termination. This is not a concept I am personally a fan of because I believe it confuses students a lot more than it helps students understand what free radical halogenation is and what is going on. But that doesn't mean you should completely ignore it. Okay, I still want you guys to at least learn about it in lecture, and if there's still more confusions, come in, drop in tutoring, ask your PLTL, SI, go to YouTube, look at your textbook, whatever you can. Okay, take ownership of your studying. Okay. So I'm not going to get into that because I don't think I should confuse you even more. What I will talk about is something called free radical halogenation, which is the second half or the other part of chapter 4. Okay, and we're actually almost done with chapter 4. So the first one. So let's think about that term real quick. Free radical. That means a radical that is not necessarily bonded. That it's by itself. Sorry, it's bonded to a carbon or some atom, but it's not committed to anything. It's bonded to a single atom. It hasn't created a bond. Okay, and halogen. Okay, stands for obviously halogens, which is group 7, which is you have your fluorine, chlorine, bromine, iodine. Okay, and halogenation means the act of bonding a halogen to another molecule, to an R group. Okay. All right. So the two main ones we are going to talk about are chlorine and bromine. Okay, specifically the term is called chlorination and bromination. Okay, so chlorination is not selective at all. Okay, chlorination is going to be exothermic. I'm not sure if these words mean anything, but just in case, you have to know, in case you get a conceptual question. Chlorination is going to be exothermic, and bromination is going to be endothermic. Okay. Now chlorination, like I said, before that, let's quickly draw fluorine, chlorine, bromine, iodine. Okay. As you go down, you increase selectivity. So this is most selective. Okay. And this is the least selective. Okay. But we mainly talk about chlorination and bromination. Okay. So between chlorine and bromine, if I ask you what is more selective, you are going to answer bromine. Okay. And if I ask you what is less selective, you are going to answer chlorine. Okay. Now let's talk about what selective means. Okay. Selective means is if I give you a bromine atom and I want you to bond that to any structure I give you, where on that structure is that bromine going to bond or want to bond? Okay. So if I give you both bromine and chlorine and a R group or any structure, the bromine is going to be very picky and it's going to choose a single, the most optimal position to bond to. Where chlorine will bond to every single available position. Okay? So bromine, okay, I was going to use an analogy, but I realized it might be a little bit inappropriate, so I'm not going to use that. Basically, bromine is more selective and chlorine is less selective. I believe you guys know what analogy I'm talking about. So if that analogy helps, stick with it. Anyways, so let's look at this example we have, and we're doing chlorination first. And then the example below is also the same example, but with bromination, okay? So the first step in a free radical halogenation problem is going to be identifying where your radicals are, okay? And a radical exists wherever there is a hydrogen available, okay? And let me type that because that's very important. Okay. A radical okay. So everywhere there is a hydrogen, you are going to place a radical. Okay, and again, a radical looks like a dot, so it is very easy. And you're only going to place a radical for unique hydrogens. Okay, so if there are if there's any type of symmetry, whether it's a line symmetry or rotational single bond symmetry, you are going to place a single radical for unique hydrogens. Okay, and for methyl, there's 3 hydrogens, right? You're only going to place 1 dot for all 3 because they're all the same signal. Okay, so I'm going to place a dot here, 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 right here, right there, right there, right there, and right there. Okay, so notice how I did not put a bond radical right here because this radical and this radical are the exact same because there is rotational symmetry on this single bond. Okay, that rotation, this methyl group can easily be on that side and it will be the exact same thing. That's why there's only 1 unique radical there. Okay, so that is the first step. Okay, I guess I can write this. So first step, find all radicals. Second step, label all radicals. Okay? Now, when I mean label, I'm talking about all of these. I'm talking about, is it benzylic? Is it allylic? Tertiary, secondary, primary, and methyl. Okay? What position is my radical on for every single position? Okay? Now, this is going to take a little bit of practice, but I'm going to speed run this because for time's sake. Okay? So this is a primary, but it is vinylic, V for short. This is secondary. Let me fix that. Okay. So this is secondary allylic because it is one carbon away from the double bond, which means resonance. Okay, resonance will come into play in every single unit. You cannot forget that concept. You cannot forget the concept of acidity and hybridization. Okay, all of those are very important. This is secondary, but it is too far away from my double bond, so there's no resonance, so it's not allylic. This is going to be a tertiary position, primary, secondary, tertiary, primary. Okay? So those are all my unique positions. Okay? Now notice I have several secondaries, several tertiaries, several primaries, and then I also have unique ones where it's secondary allylic, secondary vinylic, primary vinylic. Okay? So something I forgot to add right here for both of these. Well, I don't know about negative charge, but for this one, vinylic is at the very end. Vinylic is very unstable because there's no resonance involved. Okay. So looking at all of these positions and looking at my radical trend, guess where the most stable position is? Actually, we don't care about most stable position because we are doing which one? We're doing chlorination. And chlorination does not care. It will bond to every single person. Okay? So chlorination is that person who gets along with everyone. Okay? See, that is a better analogy than where I was going with. Okay? Chlorine will bond to every single one because it does not, it's a very friendly person. Where bromine is very selective, you know, they like to hang out with only a single person. Okay, they want to be friends with a single friend, and they'll be best friends with that single person. Okay, so everywhere we put this, we're gonna add a chlorine group to it, except for my vinylic positions. Okay, you don't ever bond to a vinylic position because it is so unstable. The likelihood of a chlorine or any atom bonding to a vinylic position, excuse me, is very, very low. Okay, and I would double check that because I'm not sure if that's true. I'm like 90% sure it's true, but there's a 10% chance that your professor may uh, like for chlorine to also bond to a vinylic position, even though it's unstable. Okay, so to redraw this, or the problem will state, it'll give you a molecule and it'll say draw all chlorination products. Okay, okay, and then your answer should look like this. Let me draw it over here. You are going to redraw all. It's similar to resonance where you have to draw multiple aspects, but you don't have to draw like the arrows because you're not resonating. So okay, so the first one, I'm going to draw a chlorine right here. second one, I'm going to draw a chlorine right there. Third one, I'm going to draw a chlorine right there. Fourth one, I'm going to draw a chlorine right there. Fifth one, I'm going to draw a chlorine right there. Sixth one, I'm going to draw a chlorine right there. And then lastly, the final one, seventh, I'm going to draw a chlorine right there. Okay, so for this problem, I had 7 different products, okay, of chlorinated products. So I have to redraw every single chlorinated position 7 different times, or as many times as there's positions, okay? Let me just quickly double check. So there's 4, 7, yes, okay? Now, additionally, sometimes they might ask you the most stable chlorinated product, but in most scenarios, they won't ask you that. The way of asking that is just asking what is the brominated product, which is saying the same thing, okay? So let's look at bromination for the same structure. Again, bromine is going to be very selective. It wants to be best friends with a single atom, a single position, okay? So looking at all of these positions, all the ones in the red, and looking at the trend, let me know or try to guess where the most stable position is. We have tertiary, secondary, primary, secondary vinylic, primary vinylic, secondary allylic. Okay, if you guessed secondary allylic, you would be absolutely correct. Okay, because this is the only one that has resonance, so this is going to be the most stable radical position. Okay, and obviously the first step is to have that radical of bromine bonded to the other radical. Okay? All right. So again, comparing chlorine to bromine, chlorine is going to be very not selective. It will bond to every single position, where bromine is very selective. It will do a single product. So bromine, you'll get a single product. So single products, okay? And chlorine, you'll get multiple products. All right? So that should be the end of chapter 4. It is going to be the free radical halogenation. It is going to be the stability of carbocation, carboanion, and radicals. It's going to be about bond dissociation energy, which is opposite of radical stability. And it is also going to go into initiation, propagation, and termination. Okay. So please review all of that. I'll zoom out as much as I can. If you guys want to take a screenshot, that's all of stability. And this should be, this should be all of free radical halogenation. Okay? All right. So next up we have chapter 6. And I'm only going to briefly introduce SN1 and SN2, keeping mind of time. And then next week we'll go in depth of SN1, SN2. Okay? So first off, SN1, SN2 means substitution. And E1 versus E2 means elimination. Okay? So what are you substituting and what are you eliminating? Okay? So let me give you an example problem. All right, so this is an example of SN1/SN2, okay? And the first thing you have to realize, or this is an example of all four mechanisms, okay? You'll have a page full of reactions, 2 pages, however many pages of just reactions, okay? And this is an example of a reaction, okay? You have your substrate, your starting point, you have what you're reacting with, and you'll have your product, which you'll have to draw out, okay? Or unless it's multiple choice, then I guess you won't have to draw it out. Okay, so there are multiple parts to this reaction, okay? The first thing is so this is called your electrophile. Which means electron loving, and I'll explain why it's called that. This is called your nucleophile. So remember when we did our periodic beam trend? The N stands for nucleophilicity, okay? So nucleophile, and I did definitely misspell that, nucleophile means nucleus loving, okay? And that's not a very good, definition of nucleophile. But phile means loving, right? So electrophile and nucleophile, those are your two components, and then you obviously combine them to get your product, okay? Within the electrophile, this part right here is your leaving group, okay? So we'll abbreviate that for LG, okay? LG stands for leaving group, okay? In this unit, or really in OCHEM, your halogens are going to be good leaving groups, okay? Halogens equals good leaving groups, okay? So let's think about that for a second. Why are halogens a good leaving group, you might ask? So halogens have 3 lone pairs and 1 radical, right? So they are always wanting to find an extra electron, right? They're always wanting to leave to bond to something else. And I'm not exactly sure if this is the right way of thinking it, but this is how I make sense. Okay? So, and of course, a reminder of all your halogens, you have fluorine, bromine, chlorine, bromine, and iodine. Okay? So all of these are good leaving groups. Okay? Now you might ask, what is the better leaving group? Okay? Is it iodine or is it fluorine? Okay? So for leaving groups, it's gonna be iodine. Iodine is gonna be the best leaving group. And for free radical halogenation, fluorine is going to be the best in terms of fluorine is going to be the least selective. Okay, so I don't know if that thought process makes sense, but let's focus on leaving groups. Okay, let me erase that. Okay, so iodine is going to be the best leaving group. Okay. And it also has to do with size, actually. Okay. Actually, I'm not sure. So it's size and acidity, kind of. Okay. So when the leaving group leaves, I am taking its electrons with me. Okay. So the leaving group, when it leaves, it will contain a negative charge. And then what I'm left with is, so if I have a negative charge on my bromine, my rest of my electrophile will have a positive charge. Okay, that is why this is called my electrophile, because it needs electrons, right? So it's gonna love electrons, okay? Because it's lacking electrons, it's gonna want electrons, okay? And that is where my nucleophile comes in, because it is a source of those electrons my electrophile is craving, okay? So in electrophile, a halogen leaves to create your positive charge, okay? So you're left with a positive charge for your electrophile, and your nucleophile is going to be the source of a negative charge, okay? So how do I get these products to look like, to get a negative charge, right? So first, let's define some of these components. This is your nucleophile, and we are going to abbreviate nucleophile as NUC dot. And this, the compound underneath your arrow is always going to be your solvents. Okay, and we'll talk about what the solvent means and how it impacts this reaction. Okay, your nucleophile is NaOCH3. Okay, almost all of your nucleophiles will contain either a sodium or potassium, or it will contain a hydrogen. Okay, so if your nucleophile contains a sodium or potassium, it is going to be, sorry, I don't know why that's happening. It is going to be a strong nucleophile. Okay, if your nucleophile contains a hydrogen, it is going to be a weak nucleophile. Okay, so sodium and potassium, if you go back to general chemistry, are strong electrolytes. Okay, and strong electrolytes, or maybe the strong. So you have strong electrolytes and weak electrolytes. Okay, but a better terminology would be ionic bonds and covalent bonds. Okay, ionic bonds contain a full positive or a full negative, where covalent bonds, and again, maybe I'm getting something mixed up, and if I am, please correct me or please ignore me. Covalent bonds have a partial positive or a partial negative charge, okay? So when my bond between sodium and OCH3 dissociate, that's the term we're going to use. So when this dissociates, okay? Dissociates obviously means separation. When they separate, I get Na positive and OCH3 negative, okay? So this Na is actually going to bond to my bromine, okay? It's going to make NaBr, okay? Which is going to be a solute, I think. Okay, so that will create a ionic bond with my leaving group, okay? The sodium, potassium, or hydrogen that left, okay? Now what I'm left with is a negative charge with OCH3. That negative charge is going to bond to my electrophile, okay? And that will create this product right here. So this is the final product and answer to my reaction, okay? So a couple of things. First thing is my stereochemistry change from a wedge to a dash, okay? Second thing is I bonded directly from my oxygen and not my carbon or hydrogen, okay? So where you bond is definitely important. Third thing is we haven't decided if it's SN1, SN2, E1, or E2, right? But with what I kind of told you, hopefully you guys will start to understand or narrow it down, okay? But to kind of give you the answer, it is going to be SN2, and it is, so SN2 is substitution, right? So we substituted the leaving group with our nucleophile. And elimination, we are eliminating our leaving group and a hydrogen to create a double bond, okay? And we'll talk more on that next week. But for this week, we're gonna find a stopping point and yeah. So here, if you guys want to take a screenshot, everything's on this page. I don't have to scroll or anything. Sorry for all the technical glitches and interruptions in between. So if you guys enjoyed all the little diagrams in chapter 4, I'll continue that for the rest of my weekly reviews. So hopefully it'll give you a little bit of structure and it's more visually appealing, and these reviews are more, useful and a good learning experience for your OChem knowledge. All right, so next week we'll review SN1, SN2, and we'll talk about E1 and E2. And I have a chart for all of these. And I'll talk about nucleophile and solvents and all that again. I kind of already mentioned about nucleophiles, so hopefully that makes sense. If not, please ask me questions. You can't necessarily comment on YouTube, so that's difficult, which is why I recommend you come live on Blackboard or in person in the library, or come during one of my drop-in hours or anyone's drop-in hours, and you can ask them, hey, I watched this weekly review, this part didn't make sense, can you clarify for me? Okay? All right, thank you guys for tuning in. I will see you guys next week.